Hey, if you've got a computer organization exam coming up, you are in exactly the right place. Over the next few minutes, we're going to slice through all the complicated stuff and build you a rock-solid foundation on how computers are put together, starting with the one question that seems to trip everyone up.
Okay, let's just dive right in. The most important concept you need to nail for your exam is this. What's the difference between the plan for a computer and the actual way it's built? Getting this right is the key to understanding, well, pretty much everything else.
And that brings us to these two critical terms, computer architecture and computer organization. The easiest way to think about it is this. Architecture is the blueprint. It's the set of rules and features that a programmer can see and use, like what instructions the computer understands. Organization, on the other hand, is how it's actually built, how all the physical parts are connected and arranged to make that blueprint a reality.
Let's break that down just a little more. Architecture is all about functional behavior. You can think of that as the user manual for the computer. It defines what the system is capable of doing. Organization is about the structural relationship, the specific nuts and bolts way the hardware is wired together to actually do those things.
Okay, let's make this super concrete with a perfect example, the multiply instruction. The architectural question is really simple. Does the computer even have a multiply command? A programmer just needs to know if they can use it or not, yes or no. But the organizational question is, how does it actually do the multiplication? Is there a special, super fast, and probably expensive piece of hardware just for multiplying? Or does the computer use a cheaper method, like just adding a number to itself over and over again? Both get the same answer, but the organization, the how, has a huge impact on the computer's speed and cost.
All right, now that we've sorted out the difference between the plan and the build, let's meet the construction crew. At its heart, every single computer is made up of 5 main functional units. Just think of them as the 5 essential departments in a company. And here they are. This diagram shows you that basic layout. Information comes in through the input unit, it gets worked on in the middle, and the results are sent out through the output unit. And right there at the core, you have 3 key parts working together: the memory, the arithmetic and logic unit, and the control unit. This is the basic floor plan for basically every computer out there.
So what does each department actually do? Well, the input unit is your keyboard and mouse. It gets information into the system. The memory unit is like a giant filing cabinet, storing everything the computer needs. The arithmetic and logic unit, or ALU, that's the calculator. It does all the math and makes decisions. The output unit is your screen or printer, showing you the results. And the control unit? It's the boss. It's the manager telling everyone else what to do and when to do it.
Now, you've definitely heard of the CPU, the central processing unit, or just the processor. You might be wondering where it is on that chart. Well, it's not a separate box. The processor is actually the central office that contains 2 of those units we just met: the calculator, the ALU, and the manager, the control unit. They work so closely together that we just group them into one component.
So let's zoom in on that processor. You can see the control unit and the ALU right there, working side by side. And you'll notice they have their own little super fast memory spots called registers. Think of these as tiny scratch pads for holding data that they need to work on right now. This whole processor is in constant communication with the main memory, pulling in the next instruction and data it needs.
Okay, so we've met all the parts, but how do they actually run a program? How does a computer think? It turns out it's a surprisingly simple and incredibly fast 2-step dance that just repeats over and over.
This right here is the heartbeat of the computer, the instruction cycle. It's so simple. First, the control unit fetches an instruction from memory. You can picture it reading the next line on to-do list. Second, the processor executes that instruction. It just does what it was told. Add this number, move that piece of data, store this result. Fetch, execute, fetch, execute. That's it. It just does that billions of times every single second.
So a logical question pops up, right? How does that instruction actually get from the memory to the processor? And how does the result get from the processor back to memory? How are all these separate parts talking to each other?
The answer is the bus structure. The best way to think of a bus is as a shared digital highway that connects all the major components. And this highway has 3 lanes. The address bus, which says where the data is going, the data bus, which carries the actual information itself, and the control bus, which is like the traffic signals, directing everything and making sure it all happens in the right order.
So we've covered the core principles, the architecture, the organization, the functional units. But how does this stuff apply in the real world? Let's zoom back out and take a look at the computer family tree.
Here, you can really see how these ideas scale up. You've got your personal computer, designed for just one person doing general stuff. Then there were many computers, which were bigger and could handle the work for a whole department, like running the billing system. And at the very top, you have the mainframe, an absolute beast for an entire company, processing huge numbers of transactions. The amazing thing is they all have the same basic functional units, but the scale, power, and of course the cost are worlds apart. And this quote just ties it all together perfectly. A company like IBM could make a whole family of computers. They could all run the exact same software, which means they have the same architecture. But the powerful mainframe has a totally different internal organization compared to the little desktop model, so it can deliver that incredible performance. And that's why understanding that initial difference is so crucial.
So, as you head into that exam, just keep this one idea in your head: the blueprint versus the building, the architect's plan, the architecture, and the builder's method, the organization. They both shape the final computer. Which leaves us with a fun question to think about. For the computers of the future, what's going to drive the next big revolution? A totally new blueprint or a brilliantly clever new way of building? Good luck with your studies!